class that because Rubia is teaching at 4, excuse me, on Tuesdays and Thursdays, it might be better to this semester to begin this class 15 minutes or half an hour earlier. Is there any objection to that from anyone? Does anyone object to meeting at 2 rather than at 2:30? Yes? Yeah, original sin on my part. 10 minutes would give me enough leeway, but...
Why don't we do 15?
2:15 is also fine.
2 is rougher.
2 is ideal.
Is there anyone who had a difficulty at 2? You have authorization when 3:30 comes, and I say, if you will allow me to run 5 minutes over time, you can scream no. It will make me feel guilty.
Momentarily.
It stays with you forever. It's the human condition. Now, are there... is that agreeable to everyone? Does anyone have a 1 o'clock class or something that would make 2 o'clock an impossible time? Okay, so we'll reschedule the class from now on to meet at 2 until 3:30. Tuesdays and Thursdays, yeah. Okay. Are there any questions about the last lecture? Everyone understood all of that? Yes. Okay.
I forgot I had a question. When you said that dz star was equal to dx dy, well, when you calculate the Jacobian, you get minus I. So why doesn't that?
Whoops. What part of the lecture was this?
Well, it was when you talked about complex n vectors and integrating over the real part and then...
It's the absolute value of the Jacobian that comes in.
Oh, okay. That's...
I defined dz star to mean dx dy.
Oh, I didn't realize that was the definition.
Now, at the end of the last lecture, I made an assertion that one could use for a field theory defined in this manner. Was an interaction that depended only on phi, but not on its derivatives, and the source term. The z of j which is the vacuum-to-vacuum S matrix element in the presence of j, could be represented by a functional integral. I've left a space here because I left out a statement. There's a normalization constant independent of j. N is adjusted, of course, in our usual way, such that z of 0 equals 1. The normalization constant n in the functional integral formulation, as we shall see, is closely parallel to the disconnected vacuum-to-vacuum graphs which you divide out in the Dyson formula for this expression. I will, let's see, how did I do this? Ah, yes. I will first, now as it stands, it doesn't look like even for a free field theory, this is a kind of, that is to say, for the case L prime equals 0, this is the kind of functional integral we can do safely, even if you don't worry about the infinite dimensions of function space. Because instead of a nice positive definite quadratic form up here, or a form with a positive definite real part, we have a factor of I. We have an oscillating form. There is another, to make sense out of this equation, I have to add another statement to it. This equation is true if both sides are continued into Euclidean space. That is to say, that space with, of four vectors with real space components and imaginary time components, and therefore with a quadratic form of definite sign, which we discussed earlier when we were discussing the analytic continuation of Feynman integrals. I will demonstrate, in order to make this a possibly sensible statement, I will of course have to demonstrate that the Green's functions of a quantum field theory can be continued into Euclidean space, which I will then first demonstrate, and then I will prove the functional integral is a well-defined object, at least as we count well-defined in Euclidean space, and then I'll be able to show the two sides are equal. You may recall that when we were doing loop integrations, we studied the propagator in the k-naught plane and found it had poles here and here in a typical case. And therefore, we did not encounter any poles if we rotated our contour of integration onto the imaginary axis. That is to say, we could take k-naught and send it into e to the I alpha k-naught, where alpha starts out at 0 and ends up at pi, arriving at the end with a variable k-naught on the imaginary axis, defining k-naught equals I k4. Pi over 2, thank you. I'm in bad shape today. Of course, if we, this was after we had done all our shifts and so on, but even before we did any shifts, if we do this simultaneously to all the external momentum in the problem, and at the same time we rotate the external momentum in the complex plane, we rotate the internal momentum in the complex plane to preserve momentum energy conservation at every vertex, this thing obviously goes through, and we have a Feynman integral defined that has no zeros in its denominators anywhere. Everything is a square of a Euclidean vector plus a positive mass squared, and the function is not only obviously well defined, it's obviously in fact an analytic function of the variables and of the external momenta. In Euclidean, I remind you that in Euclidean space, k squared equals k0 squared minus k squared equals minus k4 squared minus k squared equals minus the natural Euclidean k squared, the sum of the squares of the four components. When we rotate our external energies in the complex plane, this of course defines an analytic continuation in k space, but on the left-hand side of our equations, we have an analytic continuation in x space. We have an expression set up in x space, and it's pretty easy to see what we have to do in x space to keep things going right in k space. As we perform this operation on k naught, on a typical position variable x naught, we have to rotate in the opposite direction. Otherwise, the expression that defines the Fourier transform would develop exponential blow-ups. This way, the phase factor in x naught cancels out the phase factor in k naught. Thus, we arrive, finally, on the imaginary x-axis, x naught equals minus I, x4. This minus sign is going to be important in making our formulas come out right. Thus, I've demonstrated, at least to all orders in perturbation theory, that it's possible to continue to define our Green's functions for Euclidean space-time separations, where the formal connection between the real variable the complex variable x0 and the real variable x4 is given by this equation. Are there any questions about this demonstration? Although it's not necessary. Yes, you had a question?
I'm just wondering, have we done everything we need to do to make sure there are no poles?
Yeah, we recall once we've made this rotation, the things we get in the contour will always be some Euclidean vector squared minus m squared plus I epsilon.
No, I mean,
And then we can drop the I epsilon,
during the rotation.
because this never vanishes in the domain of integration.
Right, have we done everything we need to do to convince ourselves in
Yes, we did that in our earlier analysis. Of course, there is also a possibility that the poles will be located at positions like this and this, a priori. But no matter where they're located, we can always make this rotation. Okay? You want a more direct argument? I can give it to you another way. I have 1 over minus space part of k squared minus m squared plus I epsilon plus e to the I alpha, either 2I alpha, k naught squared. Okay? The imaginary part of this thing, since alpha is between 0 and pi over 2, this is what we get part way along the rotation. Since this thing is between 0 and pi over 2, this complex number is always in the upper half plane, and therefore this thing has always got a positive imaginary part, which adds to the I epsilon. Therefore the I epsilon is irrelevant, and then I continue all the way over to alpha equals pi over 2. Okay? It's also possible to give a direct position space argument to demonstrate that everything can be continued to imaginary time without recourse to perturbation theory, and that's sufficiently amusing that I will give it. We want to study a Green's function in position space. That's a time-ordered product of some position x1. I'll put it in little parentheses since you won't confuse it with the tensor index. Assuming there's only, for notational simplicity, that there's only a single scalar field in the problem. For convenience, I will assume x1 naught is greater than x2 naught, greater than or equal to xn naught, in which case I can cross out the time ordering symbol since things are already time ordered. I will now explicitly put in the time dependence using the Heisenberg equations of motion. This is vacuum phi h of x1 times 0 e to the minus ih, the exact Hamiltonian, x1 naught minus x2 naught, phi h of x2 and 0, dot, 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 all the way down to the vacuum state. I can now have explicitly put in the dependence on the time variables, x naught, and therefore I can investigate what happens when I attempt to analytically continue these to imaginary times. It's convenient to introduce a complete set of energy eigenstates. And write this between every two field operators, putting in a sum over energy eigenstates. I'll just write down the first sum. Of course, there's one between every pair. N1 to, I guess, NR minus 1. X1 naught. N1, N1. Phi h of x2 naught, dot, 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 vacuum, and then a bunch of explicit phase factors to be included in the summation, e to the minus I en1, en1 dot times x1 naught minus x2 naught, etc. Okay, is everyone happy with that expression? Now, we observe that, well, the thing we want to prove is in fact trivial. x1 naught minus x2 naught is a positive number. Therefore, as I rotate this in this manner down onto the lower imaginary axis, rotating downwards, this becomes minus I times minus I, or a damped exponential. Therefore, if the sum converged when this was an oscillating exponential, it certainly converges even better when it's a damped exponential. Notice that if we had tried to rotate the other way, up to the positive imaginary axis in x space, we would have gotten an increasing exponential and would have become extremely nervous at this point. But when we go down, we get a damped exponential. The sum is completely convergent. I'll just write it out explicitly when we finish the whole rotation, e to the minus. I should say, of course, we are assuming this is a sensible field theory, so En is greater than or equal to 0. En1 x naught, x4 I should call it, x4 1 minus x4 2. And is in fact manifestly not just a well-defined function of x, but because of that marvelous damped exponential, even an analytic function of x. No matter how many times you differentiate with respect to x, you get more powers of e, but you have that terrific damped exponential keeping things from blowing up. So the left-hand side of the equation is the Euclidean generating function is a completely well-defined object. To get an idea of what it looks like, let's compute it for free field theory. Euclidean z of j when L prime equals 0. We know how to compute z of j for this theory in Minkowski space. This was our famous model 1 of our 3 models that we considered in the very early stage of the last semester. And we found there that z of j was exponential. That was the exponential of the connected graphs, minus I over 2, integral d4k, 1 over k squared minus mu squared plus I epsilon, j of k, j of minus k. This, as you recall, was simply the sum exponential of the sum of the connected graphs. The connected graphs all looked like this, where this was j and this was a propagator. We got 1 I from the propagator, 2 I's from the interaction, and a 1/2 from the combinatoric factor. And we got a 2 pi to the 4th because we always have a 2 pi to the 4th, although sometimes I forget it. It's convenient to write this in position space as, which of course we can do. I'll write it out, and then you'll see that it's obviously the right answer. dx, d4x, j of x, 1 over because multiplying by this operator in position space is equivalent to multiplying by this operator minus this operator, I should say, in momentum space. I've taken out a minus sign. Now we're ready to go to Euclidean space. Remember, the only thing that happens when you go to Euclidean space is that x0 gets replaced by ix4. This means the operator del squared equals minus grad squared plus d0 squared. No, yes, equals minus del squared minus d4 squared becomes minus the four-dimensional Laplacian, which in a perverse piece of notation I have decided to call the Euclidean D'Alembert. Also, d4x, I'm sorry, there was a minus sign here. d4x equals I spent a long time telling you there was a minus sign here, and then I forgot it, equals minus I d4 x Euclidean. Therefore, continuing this into Euclidean space, we find z of j equals exponential, the I and the minus I combine together and give us 1/2 integral d4 x Euclidean j 1 over minus Euclidean four-dimensional Laplace operator plus mu squared, and I can drop the I epsilon because that's a positive definite operator in Euclidean space and never has any zero eigenvalues j. Or, as we would call it in our supercompact notation, we consider these as vectors in a infinite dimensional vector space consisting of all functions of Euclidean 4 space. This is exponential 1/2 j del e squared minus del e squared plus mu squared to the minus 1 j. Looks like the sort of thing you might get from a Gaussian integral, doesn't it? Well, let's now check that it is the sort of thing you get from a Gaussian integral by taking the left-hand side of the functional integral equation and writing that down in Euclidean space, making the substitutions I've explained here. We will then have a Gaussian integral, and we'll see what goes. I, S of phi and j equals, well, I have S on the left-hand board, so I'll get I times a minus I integral d4 x Euclidean (1/2). I'll do an integration by parts. Well, I'm going too fast, I think. Let me do it out slowly. I'll separate out the space and how will I do it? Yeah. Sorry. Let me make an integration by parts before I go into Euclidean space. That's a little bit faster. d4x 1/2 phi minus del squared phi plus minus 1/2 mu squared phi squared plus j phi. Now I'll do the transposition into Euclidean space. I times minus I integral d4 x Euclidean 1/2 phi del Euclidean squared, because grad squared becomes minus grad Euclidean squared phi, minus 1/2 mu squared phi squared plus j phi. Equals minus sign, no, plus sign, but I'm going to take it out as a minus sign, 1/2 phi minus del E squared plus mu squared, a nice positive definite operator with a minus sign in front, just what we want when we're going to raise things up into an exponential. Phi, that's the first two terms, plus j phi. Okay, any questions? Now we have a formula for doing a Gaussian integral. In the particular case, integral d phi, now over Euclidean fields, fields defined in Euclidean space, e to the minus 1/2 phi a phi plus b phi equals, by our Gaussian formula, e to the plus 1/2 b a inverse b times the determinant of a to the minus 1/2. We observe that the integral we have to do, the right-hand side of the functional integral formula, continued into Euclidean space, n integral d phi e to the is of phi and j is precisely an integral of this form with a equals minus del E squared plus mu squared, b equals j. Therefore, it is a work of a moment, that is to say, just to do a substitution to find out what this thing is. There I peek to see if it's the right answer. There's still n e to the 1/2 j minus del E squared plus mu squared to the minus 1. I'll put the n on the other side, actually. J. That takes care of that term. And then there's the determinant of minus del E squared plus mu squared. God knows what that is, but we won't have to worry about that because it's multiplied by n, and the normalization condition that fixes n says that this thing must vanish to minus 1/2. This whole combination must vanish when j equals 0. That must equal 1 when j equals 0, so therefore this is 1. That fixes n and saves us the problem of having to compute that grotesque-looking determinant, which is very good because in cold fact that grotesque-looking determinant is infinite. But we're not going to worry about things like that. It turns out to be a reflection. Well, if you actually work it out in detail, it turns out to be a reflection of the infinite zero-point energy of the free field if you don't normal order things. But if we just close our eyes to facts like that, as we do systematically throughout this course, this is equal to 1. So we have learned how to continue things into Euclidean space in a simple example, how to do a functional integral of an interesting sort in a simple example, and we have verified the assertion that sits there on the top of the left-hand board in the simple case of a free field. Are there any questions about this? Yes, sir.
How would you define a determinant in the continuous dimensional case?
It's not really continuous dimensional. Oh, how should I put it? It's, well, firstly, we could always introduce a discrete basis, compute this thing as an infinite matrix in a discrete basis, okay, and do things that way. However, there is a way of getting around it and writing the determinant in a continuous basis directly. The trick is to use this formula. This has got nothing to do with anything, but I'll tell you. Determinant of A is exponential trace log A, a formula that's manifest if you write A in the diagonal form. Okay? Now, You know, in a continuum basis, say if we take a basis for functions of force space consisting of plane waves, trace A equals integral d4k k a k. Okay? And then in this case, where this is a diagonal operator, proportional to, with k's as its eigenvalues, this is trivial to evaluate and is, of course, infinite because it's got a delta 4 of k in it, of log a, trace log a. Then it's infinite again because the integral over k blows up. But nevertheless, it's in principle an evaluatable quantity, and if it weren't as disgusting as that, that's how you would evaluate it. Okay? The infinity from the delta 4 of k just turns out to be a volume times time factor. The infinity from the integration over k, if you work everything out, just turns out to be the sum over the infinite number of virtual oscillators. It's just, what it really is just Euclidean, this infinity is just Euclidean continuation of the phase factor that comes from the 0-point energy of the free field. But I do not, I'm happy. Who cares? I can always run over time. I'm happy, I did not plan to, but I'm happy to discuss this in more detail if you want more information. However, we have verified our formula for the case of a free field. It is now trivial to verify the formula for the case of an interacting field. I would do that by showing this formula is precisely equivalent to Dyson's formula. Dyson's formula says z of j is a normalization constant, which I'll call n prime, so you won't confuse it with the n I've already introduced, times the bare vacuum expectation value of the time-ordered exponential of minus I times the interaction Hamiltonian, integrated dt, which in this case becomes plus I, integral d4x, L prime of phi I, plus j phi I. These are interaction picture fields. And the bare vacuum on the other side. That's ordinary perturbation theory. Before Wick's theorem, that was the formula we used. The normalization factor here is, of course, chosen to make this thing equal to 1 when j equals 0. Now, I can write this in the following form. Perhaps I'd better put the x in here explicitly. This equals exponential. I'll use exactly the same trick I did for evaluating a polynomial times a Gaussian. I, L prime of minus I, d by dj, let's say, of y, d4y. This is like summing over all variables if it were a finite dimensional space. Bare vacuum, time-ordered product, exponential, integral, d4x, I, j, phi I, j of x, phi I of x, bare vacuum. The reason is very simple. It's the same trick as the Gaussian. Whenever I differentiate with respect to j times this exponential, I bring down a phi inside. Therefore, if I have a function of differentiation with respect to j, bringing it inside and differentiating the exponential, I get the same function of phi in front. Is the formula clear? It needs an n prime. But aside from that, is it clear? Are people baffled by this notation? Okay, perfectly clear. Okay, the time ordering takes care of itself. The derivative is just a derivative operator of a function. I can bring it inside or outside the time ordering, and once it's inside the time ordering symbol takes care of the phi's all being rightly timed order. This, of course, aside from a possible shift, this, of course, n prime exponential I integral L prime minus I d by dj of y d4y times a quantity I can call w naught of j, the thing I've computed before, the z naught, excuse me, the z for a non-interacting field. Okay. This takes care of the left-hand side of the functional integral expression. Now let's turn to the right-hand side. N integral d phi e the I, free part, which I'll call S naught of phi and j, e the I, integral, let's call it d4y. Why have I put square brackets here? Because I love to confuse you. d4y, L prime of phi, of y. S naught is the part, the remaining part, the free part, and the part with the source. Now, I can do exactly the same trick. S naught of phi and j is the free part plus j integral j phi d4x. It's got the same structure. I can turn a function of phi into a derivative with respect to j. By differentiating with respect to j, I bring out a function of phi. So this is e to the I integral d4y L prime of minus I d by dj of y, and times integral d phi e to the I S naught of phi and j. It's the same trick. I've just done it over again. E to the I phi j is e to the I phi j. In one case, it's interpreted as an operator inside a time ordering symbol. In the other case, it's a function of C-normative fields inside an integral. But the trick is the trick. But this thing here, of course, is the integral we just did at such great pains. And we showed it gave the right answer for the free field, aside from a normalization factor, which I'll call n naught. Is everyone happy with that? I guess to be consistent, I should call it n naught to the minus 1, huh? Because it was n times the integral that was supposed to be n z. Now, if we scrutinize the left-hand board, the central board, and the right-hand board, we see we have exactly the same expressions, provided we choose n prime equals n over n naught, which is obviously the right choice in both cases, since if in one case it makes the thing equal 1 when j equals 0, in the other case it will make the thing equal 1 when j equals 0. Thus, I have proved the startling assertion I made at the end of last lecture. You can, for this particular kind of interaction, represent the generating functional, the thing that tells you everything you want to know about the theory, in terms of a functional integral. Yes, sir?
You started using subscript not that started to confuse me. I thought that you're calling it not the same as what you used to call it.
Yeah, that's right. I just put a naught on the previous problem, so you'll know that was the result of the...
You were confused when I asked why n over n naught is not equal to 1.
No, n naught is a normalization factor we computed before I erased this board. I will call the quantities associated with the free field problem, which we did before, by a naught. Yeah, and so's this one, in fact. They're all infinite, but we don't worry.
Well, in that case,
If you put things in a box and put in an ultraviolet cutoff, they're all finite.
okay, I'm just getting a little...
N naught and Z naught are the things that were computed.
How about N?
N is some new normalization factor. There'll be it's here in the Dyson formula. You know there's a new normalization factor. There are all sorts of vacuum-to-vacuum diagrams you've got to
The
do.
extra one isn't N prime.
Yeah.
I know.
It doesn't matter. There's just in each case some overall normalization factor, and if the two things are equal aside from a normalization factor, and if the normalization factor is chosen to make them equal when J vanishes,
Yes.
that is to say equal to 1, you don't have to worry about keeping track of the normalization factors. Thank you, Diana.
I tell you what, since they're all infinite anyway, I'll just forget it.
The fact that they're infinite is not relevant.
Yeah, I know, so that means that they're not relevant themselves.
No, they're held together. They are linked together by the fact that on this side n prime is chosen so that z equals 1 when j equals 0,
Yeah.
and on this side n is chosen so that z equals 1 when j equals 0.
Oh, I understand.
Okay. Okay. Therefore, we've shown they're equal up to a possible, aside from a possible difference in scale, and since at the same point they're normalized to be equal, to wit to be equal to 1, there is no difference in scale.
Okay.
Okay, are you now happy? I'm sorry. I told you I was in bad shape today. I'm going to give it, if you think this part of the lecture is bad, wait until the next 10 minutes. Yeah. By the way, I should remark that after giving you this long sermon and song and dance about doing everything in Euclidean space, I have blithely been manipulating my integrals here in Minkowski space with the eyes up there. This is a bad habit that I will persist in throughout this discussion. I will always, and to avoid the perfectly straightforward but perfectly tedious procedure of rotating into Euclidean space and out again, I will always just manipulate my integrals as if they made sense in Minkowski space. In all cases, it will be trivial to do things carefully by going into Euclidean space and out again. If we ever run into an ambiguity in the course of a Minkowski space integration, then I will retreat and do things in Euclidean space carefully to see if I can get rid of the ambiguity. I should remark that such ambiguities can occur. This is a remark I should have made earlier. If we had attempted to blithely evaluate our original functional integral for the free field in a Minkowski space, we would, of course, have, and used our formulas without worrying about whether they made sense or not, we would have obtained not the inverse of the Euclidean Laplace operator, but the inverse of del squared plus mu squared. Now that's in fact an ill-defined object. We've got to stick an I epsilon in it to make it a well-defined object. And there would be nothing in our functional integral formulas to tell us whether you put in a plus I epsilon or a minus I epsilon. The I epsilon is introduced by continuing automatically by the process of continuing back from Euclidean space to Minkowski space. We know which way we've got to continue back on general principles, and that puts in the I epsilon. In the functional integral is properly done in Euclidean space where there is no ambiguity in finding the inverse of the operator. Are there questions about that? I should say this pile is not a problem set, which is good because it's thick. It's I gave some lectures at this at a Sicilian on this subject, among other things, at a Sicilian summer school 3 years ago. The lectures are in English, not Sicilian. And it's a useful reference, so I had 50 copies Xeroxed up to distribute to those who are registered in the class first, please. I think there are more than 50 people in this room at the moment. Yeah, looks like it. Anyway, if you are registered in the class, take a lecture till 4:30. That's right. Those who stay can get a copy. Pick up a copy. Otherwise, borrow one from a friend and Xerox it for yourself. Now, the formula we have obtained can be trivially extended to more general cases. There are some trivial extensions. For one thing, of course, it was only notational laziness that made me do this for a single scalar field rather than for a set of scalar fields. And the same thing would be true if I had an L of the form involving a sum over n fields labeled by phi a plus some non-derivative term. Guess I'll call it minus u phi 1 to phi n, a mass term and a non-derivative interaction term. There again, I would, of course, by the same reasoning, define S of phi 1 j1 dot 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 as integral d4x L plus ja phi a, one source for each field. And of course, I would have to integrate over all the fields, and I would get z of j1 dot 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 equals vacuum S vacuum in the presence of j equals integral product integrating over all the fields d phi a e to the I s of phi and j. If I have 32 fields, I have to do a 32-fold functional integral, but otherwise there's no difference. Likewise, if I have complex fields in the game, I can always assemble these real fields pairwise to make complex fields. And if I do assemble them in pairs to make complex fields, phi 1 plus and minus I phi 2 over root 2, of course, and then I just write d phi 1, d phi 2 as d psi star, d psi, where psi is built out of phi 1 and phi 2 in the usual way. So I can integrate directly over complex fields, not a great generalization, but nevertheless a convenience if I happen to have a Lagrangian that's conveniently written in terms of complex fields. Also, of course, I hope you will trust me when I say there was nothing particular in the four-dimensional nature of space-time in any of these manipulations, and it can be extended to any number of integer dimensions. And in particular, it can be extended to one dimension, that is to say the particle mechanics, a fact that is sometimes useful. And therefore, if I have in particle mechanics, of course, I say not a Lagrangian, but a Lagrange density, L equals 1/2 QA dot, QA dot, not d mu, minus something we now call potential of Q1 to Qn. I can define the ground state to ground state Green's functions in the usual way, the ground state to ground state transition amplitude or whatever for this assembly of harmonic oscillators with anharmonic interactions in the presence, well, I'm sorry, I define S equals integral dtl plus ja of t qa of t. I introduce a bunch of sources, just as in field theory. And the S matrix, not to be confused with the action integral, is of course product on A dqa dvis of q and j. That's the generalization, or perhaps I should say the restriction, to no space dimensions in one-time dimension. Actually, the particle language, although I said it was a restriction, is more general than the field language, because if I allow the set A to run over an infinite set, say the Fourier components of the fields or something like that, I can always think of a field theory as a special case of a particle theory. And this form of the functional integral formula we have proved is in fact more general than this form, because this form only requires a restriction on the way the time derivatives of the fields enter the Lagrangian. How the space derivatives enter the Lagrangian is irrelevant. That's just a complicated interaction between the Fourier components, but it doesn't involve time derivatives. When at the end of this, at the beginning of next lecture, when I get on to derivative interactions, I will use this particle language rather than this field language because it is more general. Are there any questions about any of this? Now, there is a amusing fact that we have a functional integral representation for the generating functional in this case. And of course, we have shown that it is parallel to, in fact, we derived it from Dyson's formula. Now, Dyson's formula, remember, we went through a long song and dance to derive the Feynman rules. We used Wick's theorem, we diagrammatically represented the terms in Wick's theorem, we danced, we stood on our heads, we got the Feynman rules finally for a theory of this kind. I would like to demonstrate that you can also get the Feynman rules by directly manipulating the functional integral, just to show you something about the utility of functional integrals. To do this, I will have to derive an identity. The identity will be derived for I will first derive it for a finite dimensional vector space, an n-dimensional vector space, and then extend it by just making substitutions and notational changes to a function space, my usual sloppy method. The identity is this. Given a function, under certain restrictions, which will become clear in the course of the thing, of the gradient with respect to some n variable b, d by db is just grad. I don't know why I wrote it d by db times minus I. It looks like a momentum operator. F of p, g of b, another function of this n vector b. I will demonstrate that this can be written as g of minus I d by dx. We don't know what x is yet, but it'll get there. F of x e to the I b dot x, the whole thing evaluated at x equals 0. It may seem like a singularly useless identity since I've taken a function of one variable and turned it into a function of two, one of which is to be differentiated with and then evaluated with respect to 0, but we will see it will be useful to us. This is a typical PQ type identity. I could have written it in operator forms with p's and q's, but I've chosen to write it with derivatives. The proof is easiest to show if we assume that f and g are plane wave functions, perhaps with complex plane waves. So let me take as a typical example, f is, let me get it straight, a plane wave, where p is some number or some n vector, perhaps real and perhaps complex. G is a plane wave characterized by another number, q. It's, of course, very easy to do the left-hand side of this integral because this is an eigenstate of d by db with eigenvalue q. So this operator acting on this function just multiplies it by iq. So this is simply e to the p dot q, e to the I q dot b. That's the left-hand side of this equation. Now let's look at the right-hand side. For b here, I have to substitute minus I d by dx. So I get e to the q dot d by dx. For f, I have to substitute, for the minus I d by db here, I have to substitute x. So I guess I get e to the p dot x. And then from the formula, what I told you, I have e to the I b dot x. Once again, the thing is easy to evaluate since this is an eigenfunction of d by dx with eigenvalue p plus ib. And eventually I've got to set x equals 0. So that gives me e to the q dot p plus ib times an exponential, which is equal to 1 since I've set x equal to 0. We observe that this expression is equal to this expression. So I've proved the theorem when f and g are exponentials, and therefore by trivial Fourier transforming, I've proved it when f and g are, say, Gaussians, or when f and g are polynomials, or when f is a polynomial and g is a Gaussian, or anything like that. Any questions on this formula, aside from what it's good for? I'll show you what it's good for in a moment, but the questions on the derivation. Now, let's recall our functional integral formula. I actually have it on the board. In the case of a single scalar field, for the generating functional z of j, aside from a normalization constant, which I'm not particularly interested in, it's either minus I integral d4x L of minus I d by dj of y of x. Well, maybe I better call this z or something. I'm going to be using x's and y's in a moment. J of z times z naught of j, where z naught was the generating functional for a free field. And it wasn't minus I, it was plus I, wasn't it? And it wasn't L, it was L prime. And I should have stayed in bed today, but I think that takes care of all the z naught of j I would like to write out a little bit more explicitly than before. Equals exponential 1/2 integral d4x d4y j of x j of y times a Feynman propagator, which I'll call delta f of x minus y. That's just shorthand for the function that we called the contraction in our earlier discussion. It's the Fourier transform. Okay, that's just the same formula we've had before. I've just written it out a little bit more explicitly than before. Now, let's evaluate this expression using this identity. It is, of course, of this form. That's what I proved the identity for. We have to introduce the dummy variable analogous to x, which we will shortly differentiate with respect to, and just to confuse you all, I'll call it phi, since there is no phi left in this formula. We've integrated over our original phi. Okay. So, this is the analog of the function f. This is the analog of the function g. X I'm going to call phi. Instead of writing differential with respect to x, I'm going to write a funny-looking little wiggly differential. That's our stupid convention when we're dealing with functions with respect to phi, but it's the same formula. So I have got to substitute for here minus I d by dx. That gives me 2 minus i's and an overall minus sign. Oops, I wrote it wrong. It's minus this. Someone should have called me. Remember, it was minus I in the expression. That cancels out that minus sign. I forgot to write down. So I get z of j equals some normalization factor, exponential, plus 1/2 integral d4x d4y variational derivative with respect to phi of x, delta f x minus y, variational derivative with respect to phi of y, acting on, now I've got to make the other substitution here, instead of minus d by db, this L prime becomes e to the I integral d4x L prime of phi. Then I've got to add the analog of x dot b, which is, whoops, I've lost my, j phi. Okay, that's the same formula transposed into a new notation. Okay, for j, for inner product, I've written integral d4x, product of two functions. For j, I've substituted, for b, I've substituted j, for x, I've substituted phi, etc. Now, this formula is in fact, yes, question.
Here's where you have two different exponentials.
Yeah, this operator, which is a second derivative term, zero derivatives, two derivatives, four derivatives, etc., acts on this function. You just look at this expression and think of it while I mumble nonsense. You may be able to see it as nothing more or less than the Feynman rules. Because what happens if we expand this out? We get a sequence of, we get a string of phi's and j phi's. We get, that is to say, we get a string of terms, which we could represent by vertices, integral d4x1, integral d4x1, with, say, if it's phi-4th theory, they have four phi's coming out of them, and then if you pull in a j phi, you get one of these. Okay, and then maybe there's another phi-4th around here. You've got to act on this thing with the differential operating. You've got to eat up all these phi's. They've all got to be differentiated. Because if they ain't all differentiated, then when you set phi equal to 0, you're going to get 0, because you got a leftover phi. Therefore, I'll indicate if I differentiate one of these phi's here with respect to this one, and another one with this one, the given term, I'll connect them together. The factor that corresponds to connecting two of them together is just the Feynman propagator. The 1/2 is irrelevant, because if I've got two phi's, I can either differentiate the first one with this and the second one with that, or the first one with that and the second one with this. And that cancels out the 1/2. So I just get, if I interpret this expression graphically, I got to connect together all the lines except those that go on to external currents somehow, and to j's, like that. Where every connection I have a Feynman propagator, etc., the usual story. I get the Feynman rules. This is Wick's theorem, written in a notation so compact that it's practically impossible to see it as Wick's theorem. But as soon as you start applying it to this exponential expanded out to any given order, you easily see that it is nothing but Wick's theorem. The operation of contraction here becomes the operation of differentiation, etc. Okay. Wick's theorem is simply our old rule that is simply in an incredibly complicated disguise, because you're working on an infinite dimensional space, the rule that seemed so trivial to you last lecture about how to integrate a polynomial times a Gaussian. Is this point clear? I screamed and mumbled, and I pointed at graphs and so on, but beneath my bestial grunts, did you see an argument? Now, that's convenient, because it means if we're evaluating a general functional integral of the form times a polynomial times a Gaussian, we don't really have to remember all of our formulas, because the rules for integrating a polynomial times a Gaussian are just like the Feynman rules. The Gaussian, whatever it is, defines a propagator. The polynomial defines vertices, and then you just stick things together a la Feynman rules. Thus, for example, if I have by dint of hard work, an expression of the following form: d phi e to the I phi a phi plus j phi. I'll write it for a single field. It generalizes trivially to many. Plus something s prime of phi, some leftover part that I'm going to evaluate perturbatively. And this is absolutely any differential operator. Okay? And this is absolutely any function of phi with 47 derivatives in it and a non-local integral kernel of 17 variables and just some horrible mess. Okay? The way I evaluate it is just by the Feynman rules. I write down naive interactions corresponding to this, and derivatives are derivatives. And there's no point about whether they commute or don't commute with time orderings, because there's no time orderings. It's just these are scalar field, classical C-number fields. Everything commutes with each other. I just write it down, and I deduce a propagator from just this object A. It's going to be the inverse of A with an appropriate factor of I, which you can readily work out. I worked it out last night, but I'll just look it up. Whatever the propagator is, it'll be the solution of A df of x minus y. This will define the propagator is I delta 4 of x minus y. The inverse operator, written as a function of two variables as an integral kernel x and y. Any ambiguities that arise in inverting the differential equation are to be resolved by continuing to Euclidean space, where the functional integral is really supposed to be defined in the first place, and that'll tell us where to put in the I epsilons. Now, of course, this I shout and scream a lot, but for the moment, this is a useless piece of information, because the only field theory in which we know, only class of field theories for which we know we can write the functional integral this way, is the class we already know how to derive the Feynman rules for. Sorry, the only field theory for which we know we can write the generating functional as a functional integral are the field theories where we can already derive the Feynman rules anyway. However, shortly at the beginning of next lecture, we'll get to a point where for more complicated field theories, we'll be able to write the generating functional as a functional integral. Once we do that, we can use this rule. We can forget all about the explicit formulas I wrote down for how to integrate a Gaussian, how to integrate a polynomial times the Gaussian, and so on. The rules are always Feynman rules. You just naively read off, once you get it in this form, you just naively read off the interactions from this. A derivative is a factor of momentum, blots, everything, just goes right through. And you naively deduce the propagator from this, or from the matrix equation that replaces it if you have many fields. Okay, is that point clear? This is one of the utilities of functional integrals. The perturbative method of evaluating any functional times a Gaussian is nothing more or less than the Feynman rules as given by Wick's theorem, where the propagators are given by the inverse of the operator that appears in the Gaussian, and the interactions are given by the thing you're evaluating. Okay, is this point clear to everyone? I will say it 3 times if need be, and maybe you'll understand it the 3rd time if you don't understand it now, but you understand it now. Okay. That's what we're getting for. That'll enable us to take care of all those terrible problems with derivative interactions and anything else if we can just beat on the theory and get it into this form. And then we can just read off the Feynman rules. Never have to worry again in our lives about Dyson's formula, Wick's theorem, anything else. This will be the magic method. Now, as an example of how this magic method works, I would like to apply it to a case where I have not yet justified it. Let me suppose it is true for the theory of massive vector mesons, a formula that we can write the generating functional as a functional integral. I have not proved that, and I will not prove it until next lecture. However, just to give an example of this algorithm at work, let me assume I have proved it, and I will attempt to construct the propagator. So, the propagator is given exclusively by the free action. That's all we got to worry about. The free action, S naught of A mu, is integral d4x, as always, minus 1/2 d nu A mu minus d mu A nu, where here I've used the anti-symmetry of this expression to hide only one of the two terms that occur here. The other one, of course, gives us the same thing. Plus 1/2 mu squared A mu. Perhaps I'd better not use A for this, because throughout here I've been using A for the operator, and that'll confuse you, so I'll switch to a script A for my vector field, just to keep you from going bananas, keeping two kinds of A's confused. Now, my first step is I've got to write this in this form. And there should have been a 1/2 here, of course. I've got to write this in this form with this operator in here. Therefore, I've got to integrate by parts on this d nu. And I will obtain this in the form integral d4x A mu times some operator, which also bears tensor indices, coupling together different components of the fields, A nu. And it's this operator I've got to invert as a matrix differential operator. By trivial integration by parts, A mu nu equals, minus sign cancels, by integration by parts, G mu nu box squared. That's the first term. The second term gives me there's a minus sign there, and I get d mu d nu. And finally, the last term is plus mu squared g mu nu. I have to find the matrix Green's function for this differential operator. That is to say, I have to find an object such that A mu nu d nu rho Feynman of x minus y is the identity operator on the whole space, delta mu rho from these indices, delta 4 x minus y, and 9. If the Green's function is ambiguous, if the problem does not have a unique solution, I'll have to settle the ambiguity by doing things by rotating, putting an I epsilon so everything can be nicely rotated to Euclidean space. Okay? Is everyone happy with this? I have just taken this general prescription, trivially generalized the case where the fields have many components, and written it down for this particular case, and actually found out what the differential operator that appears here is. Now, the computation is, of course, like solutions of all differential equations with constant coefficients, most easily done in Fourier space. In Fourier space, del squared becomes minus k squared, d mu becomes I k mu, etc. So I have minus k squared g mu nu plus k mu k nu plus mu squared g mu nu d nu rho twiddle Feynman equals I times 1, the Fourier transform of the delta function. This takes care of most of the problems, but we still have a 4x4 matrix to invert, which is not particularly easily, unless we break it up into the sum of two projection operators. Let me consider the following two operators. P mu nu transverse is g mu nu minus k mu k nu over k squared. This projects on Fourier components which are transverse in the four-dimensional sense, orthogonal to k. It is the projection operator on vectors orthogonal to k. This is the orthogonal projection operator, p mu nu longitudinal, is k mu k nu over k squared. It projects on vectors which are aligned along k. Since this thing is a linear combination of g mu nu and k mu k nu, it can be written as a combination of these transverse and longitudinal projection operators. Let's do it. And then it's very easy to invert, because you just invert the coefficients of the projection operators. A mu nu equals minus k squared plus mu squared. Thank God that's right. P mu nu transverse, that takes care of the g mu nu. And then to eliminate that, I'd better add p mu nu longitudinal with a plus sign to cancel out this, minus k squared plus mu squared. That takes care of both g mu nu parts. And then I'm left over with a k mu k nu, which is, of course, simply plus k squared times p mu nu longitudinal. Okay, that's the decomposition. I've written it out that way. Since these are projection operators, to invert, I just invert the coefficients. Of course, I also want to multiply by I and lower the indices by notational stupidity. There's an I in front. P lambda rho transverse over minus k squared plus mu squared. There's an ambiguity there, which we'll get rid of by putting things into Euclidean space. Plus I p lambda rho longitudinal over mu squared. That's the inverse. I multiply this by this, and I get I. Oh, sure. That's clear to everyone. I mean, explicitly work out. This is the inverse of this. This times this gives us the transverse projection operator times 1. This times this gives us the longitudinal projection operator times 1. The cross terms vanish. The sum of the transverse and the longitudinal is the delta, the identity matrix. Now, let's reassemble. The algebra is trivial. I have an overall I in front. I firstly have g lambda rho over minus k squared plus mu squared. Then I have plus minus k mu over k squared. That's the leftover part in that. I should write plus k mu over k squared. The leftover part in the longitudinal projection operator is minus 1 over minus k squared plus mu squared. Yes, that's right. It's this minus this.
The subscripts.
Oh, lambda rho. Thank you. And then there's plus 1 over mu squared. Now, plus, minus to make life easy for me. Now, it's very easy to combine these denominators. This whole combination is just k squared over mu squared, k squared minus mu squared. The k squared out here cancels the k squared out here. The k squared minus mu squared is a common factor. The final result is minus I over k squared minus mu squared, g lambda rho. That's the first term. Second term, the k squared has been canceled. I've got a k lambda k rho over mu squared with a relative minus sign, and the same denominator. Okay. Any questions? This is the propagator for the vector meson field, except I have an ambiguity when k squared equals mu squared, which I, of course, eliminate in the usual way. That's forced on me by the condition that it should have a rotation into Euclidean space. It's always got to be plus I epsilon, k squared plus I epsilon, otherwise I couldn't rotate into Euclidean space. Thus, if I could establish a functional integral formula, as I will next lecture, for the case of a massive vector meson, I would establish this expression for the propagator. I will establish such a functional integral formula, and therefore we shall arrive at this expression for the propagator. Now, yes, sir? I want to establish that I can write the generating functional for the theory of a massive vector for quantum electrodynamics with a massive photon as a functional integral. I have not yet shown that because it is not of standard form.
I'm just curious how much that would differ from what you've done.
Well, this is what I would have done after I did that. Once I have written it as a functional integral, I can write it in this form. Okay. Note that, let me talk on for a minute. I'll stop at 4 because of Carlos' thing, but let me stop a minute. Let me go on for at least 2 minutes more. Note that this is exactly the same general form in one sense as we found in the case of a free fermion, or for that matter in the case of a free spinless particle. For a free spinless particle, we had 1, which you could think of as the projection operator on the physically allowed state, over k squared minus mu squared. For the fermion, we had p slash plus m, which was the projection operator on the physically allowable state, over p squared minus m squared. Here we have minus g lambda rho plus k lambda k rho over mu squared, which is nothing but the projection operator on the 3 allowed transverse polarization vectors over k squared minus mu squared. So we've always got, it seems to always come out to be the same answer, although actually that's special to these cases. There are more complicated cases where it doesn't quite come out to be that. We also see that we're going to have troubles even after we derive the Feynman rules that are going to cause us a certain amount of worrying. For one thing, this thing sure as hell doesn't look as if it has a nice smooth limit as mu goes to 0. We're going to have to worry about that, and we will worry about that. For another thing, precisely because of the same term, this thing doesn't look as it behaves very nicely as k goes to infinity. This term is just aside from some extra indices, like a scalar propagator, but this term has got 2 powers of k in the numerator, and looks like it's going to screw up the renormalizability of the theory. Maybe we can't construct a renormalizable theory. We can, but we'll have to worry about it. That's in the future. At the moment, the things I have ahead of me is that I have to redeem this computation by showing that I can indeed, for electrodynamics, write the generating functional as a functional integral. And that means I'll have to tackle a problem of theories with degrees of freedom that you have to eliminate from the Lagrangian before you can write things in Hamiltonian form. And I will tackle that problem next lecture. I'm going to have to worry also about at least scalar electrodynamics, so that means I'm going to have to worry about theories with derivative couplings. And of course, I haven't said anything at all about using the functional integral formalism for fermions. That should lead us into rather peculiar waters, because we've discovered that for bosons, what you do is write things as a functional integral over classical Bosch fields. That is to say, ordinary C-number fields, the limit of quantum Bosch fields as h bar goes to 0. And this would lead you to suspect, if you were bold at guessing, that if you have a theory with fermions in it, you write things as a functional integral over classical Fermi field.